crude treatment of the pi electrons in a conjugated molecule regards these electrons as moving in the particle in a box potential. So the particle in a box potential, just to recall, is, let's say the box length is L along the x coordinate. The potential is 0 inside the box and it's infinite outside the box. The Pauli exclusion principle allows no more than 2 electrons to occupy each box level. So these are the different box levels, right? N equals 1, N equals 2, N equals 3, and so on. Now, the Pauli exclusion principle only allows 2 electrons to occupy each box level. Now, if you're looking at 1,3-butadiene, CH2, double bond, CH, CH double bond, CH2. So we have 1 and 2. So we have like 2 pairs of pi electrons. So we have like 4 pi electrons here. Now, since the Pauli's exclusion principle allows only 2 electrons to occupy a given energy level, starting with the lowest energy level, there will be 2 occupying this, and there will be 2 occupying N equals 2, right? Now, it's given that the box length is 7 angstrom, and we're asked to use this model to estimate the wavelength of the light absorbed when a pi electron is excited from the highest occupied to the lowest vacant box level of the molecular electronic ground state. So the experimental value is given to be 270 nanometers. I don't expect us to get super close to this value because it's just a very crude approximation. It's a very crude treatment of this problem. So the highest occupied level is N is equal to 2, right? And the lowest unoccupied level is N is equal to 3. Now, let's say we have this electron make a jump to here. It's going to go from N is equal to 2 to N is equal to 3. Now, we need to compute the wavelength that corresponds to this transition. This is the energy difference, and this corresponds to this wavelength. I can first cancel out the H on either side, and then I can have 3 squared minus 2 squared, 9 minus 4 is 5. It's going to be 5H over 8mL squared is equal to C over lambda. Now we need to compute lambda, right? So that is going to be 8mL squared times C divided by 5H. Because we're dealing with an electron, the mass of the electron is going to be this. And the length of the box is given to be 7 angstrom, just 10 to the negative 10 meter. L squared is going to be meter squared, times the speed of light. So when we compute this value, let's actually compute it. It's going to be 8 times 9 times 7, 49 times 3 divided by 5 divided by 6.626. So this is going to give me 319.468 times 10 to the power. I'm going to club all the powers of 10. So negative 31 minus 10 minus 10 plus 8 plus 34 from the denominator. And let's do some unit cancellation. So kg meter square per second square and the joule get cancelled. So you only end up with meter, which is right. And 10 to the power negative 9 meter is nothing but 1 nanometer. So the wavelength corresponding to this transition is going to be approximately 319 nanometer, which is definitely 102 nanometers farther away from the experimental value.